So we're just do an example here of two-dimensional motion to start us off. So let's suppose we got the floor here and we got a table. And so we have a table and we got an object sitting on the edge of the table. Let's say that the table is a height of 1.25 meters and you knock this object horizontally, and the horizontal velocity, the initial velocity is 2.56 meters per second. And so I want to know, where does it land over here? Okay, so what do we do? Well, I'm trying to find this x distance. And we know that x equals x naught plus vx naught t plus 1/2 ax t squared. Okay, now the initial velocity is purely horizontal, so I can say that v naught vector is going to be the vx naught I plus vy naught j. Now, just to be complete, it would also be vz naught k. Okay, but we're not talking about the in and out of the screen at this time. So right now, the initial velocity is purely horizontal, so that is going to be equal to 0 right now. So V naught is just going to be the 2.56 meter per second I. So it's only going to be in the x direction. Okay, now, what's the acceleration in the problem? The only acceleration is downward, and that's g. Well, downward is not horizontal, so the x acceleration is 0. Now, where do you want to put the origin? You can put the origin anywhere you want. I tend to be boring, and I put the origin where I start. So I say that way is positive x, and this way I'm going to call positive y. Okay, now why do I do that? Your book would have put the origin, your textbook would put the origin at the bottom and say up is positive. Okay, well, I don't like doing that because that makes gravity negative. I just don't like negatives. It's got too much negativity in the world anyway. So I just try to avoid the negatives when I can and keep everything positive. Okay, so if I put my origin right there, x naught is 0, so x is just going to be v x naught times time. Well, fantastic. We know vx naught, but we don't know time. Okay. By the way, this is another thing that you can sometimes do as a problem-solving strategy, is you write down the problem and then underline it in a different color. I'm having a little trouble changing the color of my stylus here, but if you could change the color, you'd underline it in a different color. So I see a lot of students, when in person, and they come to class with just a box of map pencils, all different colors, to highlight things, because then it's easy to just glance at the piece of paper and see, what do you have to solve for? Okay, so we don't know 2/3 of the things in the equation. So we say we need another equation. Well, we got other equations. We know there's a y distance here, and so why don't we look at the y equation? So the y equation is that y naught plus vy naught t plus 1/2 ay t squared. If my origin is right up here where I start, then y naught is 0. The initial velocity is only in the x direction, so the initial y velocity is 0. If I say down is positive, the y acceleration is g. So this is 1/2 gt squared. And we say, well, what do I know? Well, I know y, because that's given up here, 1.25 meters. I know g. I know 1/2. And so t is just going to be the square root 2y over g. Okay, if I plug in here for my y value of 1.25 meters, then that comes out to be 0.505 seconds. Okay, I plug that in over here, okay, 2.56 meters per second times 0.505 seconds, and so my x distance is 1.29 meters. Okay. So my problem here starts 1.25 meters high. I hit it horizontally and it lands over here, and it lands a distance of 1.29 meters over. My next question is, how fast is it moving and in what direction when it hits the ground? Okay. So I want to know what direction is it moving when it hits the ground and how fast. Well, how fast is going to be the v equations. So we know that Vx equals Vx naught plus Axt. We know that Vy is Vy naught plus Ayt. Now, initially, there is no y velocity. There is no x acceleration. So Vx equals Vx naught. In other words, the x velocity doesn't change. So the x velocity continues exactly the same speed as before, and all we're doing is we're adding y velocity. So Vy equals gt, because I said that down was positive. Okay, and so Vy is gt. So that means that Vx remains 2.56 meters per second. It means that Vy is going to be 9.81 meter per second squared times 0.505 seconds. So Vy is going to be equal to 4.95 meters per second. Okay. So that means when it hits the ground, so started on the table here, went this way, hits the ground down here. It means the moment that it hits the ground, it's got the velocity is going to be the x part, 2.56 meters per second I, and the y part, 4.95 meters per second J. Okay, so that means it's got an x part and it's got a y part. Okay, so it's moving like that. So that means if it's got an x and a y component to it. Okay, so this is Vx, that's Vy right here. Okay, so the total velocity is going to be the square root of Vx squared plus Vy squared. So Pythagorean theorem. And so if I do that, that's going to be square root of 2.56 meters per second, and then that's squared, plus 4.95 meters per second, and that's squared. Okay. Now, notice it's constantly getting faster because the y velocity keeps changing. It was 0. Remember that this y velocity is just going to be equal to gt. So when t was 0, that was equal to 0. As t gets bigger, that gets bigger. And so the y velocity keeps changing. So when it hits the ground, it's going to be 5.57 meters per second. Okay, now what direction is it moving? Well, it's got an x part and a y part, so I can find the angle there. The angle is going to be the arctangent of the y part, 4.95 meters per second, divided by 2.56 meters per second. And so that comes out to be, okay, 62.7 degrees. So what I would do is I would say that gets knocked off, hits the ground, it's moving. I would say here, we could get the x and y components like I did, or you could also say if I wanted the magnitude here, that it's going to be the magnitude and the direction. Okay, but the thing is, the direction is 62.7 degrees. Okay. Notice, if I just draw a line like that, because students want to do this, and so they say, okay, here's the y, there's the x, and so we have an angle here, phi. Phi is going to be the arctangent of y over x. So that's going to be the arctangent of 1.25 meters divided by 1.29 meters. So phi is equal to 44.1 degrees. Okay. That is not the direction of motion. So that is absolutely not the direction of motion. That is the direction from where it landed, rather from where it started to where it landed. But that is not the direction that it is moving when it hits the ground. Okay, so the direction it's moving when it hits the ground is the 62.7 meters per second. If I ask what direction is something moving when it hits, if you use the x and y values, the position values to find the answer, it is going to be absolutely wrong. Do not even expect partial credit for that, because I am telling you right now that is wrong. If you want to know how is it moving, use the angle for the moving components, the Vx and the Vy. So you could write this as 5.57 meters per second at an angle of 62.7 degrees. Well, what's 62.7? Below horizontal. Don't just say 62.7, say how you're measuring 62.7. You could write this differently too. You could write this as the velocity is 5.57 meters per second at an angle of 27.3 degrees from straight down. So it's from the downward vertical. So instead of going straight down, it was an angle of 27.3 degrees from straight down. So either one of these two ways of writing it is a legitimate way of answering that question, how fast and what direction was it moving? This is absolutely wrong. So don't do that.